And I'm going to start with ions of elements. So on Thursday of last week, we concluded the information by discussing the atoms of the elements that were neutral. When we're looking at atoms of elements, the periodic table has some of the information that you need regarding the atom of the element. The first piece that you find on the periodic table is going to be the atomic number. So potassium, for example, is atomic number 19. That 19 is not only the atomic number Z, but it is also the number of protons and the number of electrons in an atom of an element that is neutral. It has the symbol. Your symbols, for the most part, are going to be, they're either one or two letters. The first letter is always capitalized, the second letter is always lowercase. They represent the, for the most part, the letters represent the element symbol. But there are exceptions to that, potassium being one, sodium being another. These elements are some of the elements that were discovered early in time, and therefore they wind up being, their symbol is actually related to, for example, their Latin name, or their Greek name, or something of that name. Now, on the periodic table you'll receive on the exam, you'll also have the name of the element. And then finally, on the periodic table, you have the average atomic mass. We're going to talk about how this number comes into play, comes into being later on. Now, again, what we've been talking about are neutral atoms of elements, meaning the number of protons equals the number of electrons. The number of protons has to equal the number of electrons in order to make the atom neutral, because protons carry with them a positive charge and electrons carry with them a negative charge. For every positive charge, you have to negate it with a negative charge. And that is why they are neutral or have zero charge. Now what I'm going to do is I'm going to introduce the ions of the elements. So, ions of elements are the result of the gain or loss of electrons. A cation is going to be a positively charged ion that results from the loss of electrons. And your anion is going to be a negatively charged ion that results from the gain of electrons. Once you make a cation and an anion, these ions are attracted to one another electrostatically. Basically, you could think of a magnet. You got a positive end of a magnet and a negative end of a magnet. And when they're brought in close contact, they're attracted to one another. The same thing goes with our cations and our anions. When they're brought in close contact, they're going to be attracted to one another. So again, when we were looking at these atoms of an element, we are looking at the gain or loss of electrons. Notice I never say the word proton. It's not, the protons don't change. We're talking about a gain or loss of electrons. So for example, sodium here, a neutral atom of sodium has 11 protons plus 11. It has 11 electrons minus 11. So between that, you have a zero net charge, hence it's neutral. Now, sodium will lose its valence electron to form a sodium ion. In this case, again, you still have 11 protons. The protons determine that it is sodium. So you still have a plus 11. But once you've lost that valence electron, you now only have 10 electrons or 10 negative subatomic particles. So you have a plus 11, a minus 10, which gives you an overall plus 1 charge. That plus 1 charge is illustrated as a superscript to the right. Now, a lot of times when we have a 1, we don't include the number, but if we had a 2, 3, or 4, we would include the value as well as the sign. When we do the formation of an anion, here is a chlorine atom. We have chlorine that has 17 protons. And if it is completely neutral, it'll have 17 electrons. The proton is positive, so that's a plus 17. The electron is negative, so that's a negative 17. A plus 17 and a negative 17 equals 0. Now, chlorine gains an electron. So, again, this has an error, and I just saw that. Ignore. It gains an electron. Does the protons ever change? No, so it still has to have 17 protons. But it gains an electron, so it winds up with 18 electrons. A plus 17 and a minus 18 equals a negative 1. So chlorine gains an electron to make chloride. We represent the charge as a superscript to the right of the element. So with respect to our ion symbols, we can get very technical with the ion symbols. We can tell you fluorine has an atomic number of 9. This particular fluorine has a mass number of 19. And it carries with it a negative 1 charge. This information gives us a lot of details about fluorine, because if the atomic number is 9, it means it has 9 protons. The 19 is the mass number, which is the protons plus the neutrons. So if we subtract out the protons, we are left with 10 neutrons. This negative 1 tells us that we have 1 additional electron. And so we would have 10 electrons. Yes.
In the video, you said that when you're writing like the ion notation, the number comes before the positive or negative sign, can it be either way?
Okay. So when I write, I didn't actually create these. When I write it, you are going to see me put the number first. When I'm talking about a charge. The reason I do that is later on we're going to talk about oxidation states. And with oxidation states, we flip it so that we can recognize the difference between a charge and an oxidation state. Does it actually matter? Not really. But it is common notation to do it that way, where we can separate an oxidation state from a charge. Okay, so oxygen. Its oxidation, its atomic number is 8. It has 8 protons. the mass number is 16. 16 minus 8 means it has 8 neutrons. And this oxygen is a -2 charge, meaning it has 2 more electrons. So it has 10 electrons. So there's a lot of information. Now, on Friday or Thursday, you picked up a periodic table where I had marked it. And it showed the ions. This periodic table. I know, I gave you lots of things Thursday. There is a very nice diagonal that can be drawn on the periodic table. Starting with boron and just making a diagonal. What you will notice if you look at that periodic table, everything to the left of that diagonal carries a plus charge. Everything to the left of that diagonal is going to form cations. Everything to the left of that diagonal are called metals. And metals form cations. Now going back to this diagonal, you will notice that everything to the right except for the noble gases forms anions. Everything to the right forms anions. That's because your non-metals, which are to the right of that diagonal, form anions. We're going to discuss the reason for this a little bit more once we get into electron configurations. Because that is actually what tells the story of who makes a cation and who makes an anion, is electron configuration. But in general, I just wanted to point out that everything to the left tends to form positive charges and everything to the right, and some of the things in the diagonal tend to form negative charges. Now you will notice that noble gases have no charge. Boron, carbon, and silicon have no charge. That's because the noble gases, until you get to xenon, don't even make a compound. And they definitely don't make ions. Boron, carbon, and silicon tend to not form ions either. They may make polyatomic ions, which we'll discuss later, but they themselves, as an element, do not form an ion. So, again, the thing you were supposed to note and thing I kept emphasizing is that the atomic number did not change, and therefore the number of protons has to be a constant. The only thing you can manipulate are your electrons. That is because the electrons are responsible for the element's reactivity. They're the only thing that can be manipulated by the loss or gain of. Therefore, the formation of an ion only impacts the number of electrons in the atom. If you have a positive charge, it means that there are fewer electrons present. Whereas if you have a negative charge, it means there's a greater number of electrons present. Again, the only thing you're manipulating is the electrons. So let's look at how it's going to look on the exam. You're going to have a table that you have to complete. Okay, so let's look at N3 minus. Nitrogen is element number element number 7 on the periodic table. So what does that mean? 7 protons. A negative charge results from the what of electrons? Gain or loss? Gain. So if we have 3 minus, it means we gained 3. So how many electrons does nitrogen have? 10. And it is a 3 minus charge or a minus 3. At this point, it won't matter. The next one, it has 26 protons and 24 electrons. What does the proton tell me? Its atomic number. And so element 26 on the periodic table is iron. Now, you can take that plus 26 and you have electrons, which are a negative 24. Plus 26 minus 24 comes out to be plus 2. So therefore, the iron is a 2 plus charge. Take a moment to do the next 3. Okay. So it's silver. AG 47. That's its atomic number, so therefore that's the number of protons. It is plus charge. Plus charge results from the loss of electrons, meaning there's fewer by that number. So there would be 46 electrons, and it's a +1 charge. Selenium, Se. Look and find Se. It's element 34. That means that has to be the number of protons. Anion results from the gain of electrons. Therefore, you have 2 extra electrons for your 2- charge. And then on this last one, plus 35 minus 36 is a 1- charge. 35 is bromine, so it's a bromine minus. Questions? Then let's move to the average atomic mass. As I've mentioned multiple times, this number is the average atomic mass. It is not the mass number. It is, you cannot use this to determine the mass number. You cannot use this to determine the number of neutrons. This is the average atomic mass. The average atomic mass takes into account all naturally occurring isotopes of an element. And their abundance. Carbon is 12.01 for its average atomic mass. That is because roughly 99% of all carbon atoms are carbon 12. But it's not perfectly carbon 12. So around 1% is carbon 13. That is naturally occurring. What do I mean if I say it's naturally occurring? What it means is if I go dig up a sample of carbon and I analyze it using mass spectrometry, 99% of that sample I just dug up is going to be carbon 12, meaning it's going to have 6 protons and 6 neutrons. But the other 1% that I dig up is going to be carbon 13, meaning it's going to have 6 protons and 7 neutrons. So again, this number is the average atomic mass, and it takes into account all naturally occurring isotopes and their abundance. It can be calculated as the average atomic mass is equal to the sum for all naturally occurring isotopes of the isotope mass times its abundance. Notice I say abundance, not percent abundance. A lot of times we record percent abundances and we have to take it out of the percentage and put it into strictly abundance to be able to put it into this calculation. But again, this, and I did provide this equation on the test, even though originally I did not provide it on your formula sheet. I did wind up including it on the test. Again, the average atomic mass is equal to the sum over all naturally occurring isotopes of the isotope mass times its abundance. The easiest way to deal with this is to see it in action. So that's what we're going to do next. So, as I mentioned, carbon, if I go dig up a sample of carbon, roughly 99%, it's actually 98.93% is carbon 12. But 1.07% is carbon 13 that has a mass of 13.003355. Now, technically, there are 3 isotopes of carbon. There's also carbon 14, but carbon 14's abundance is so negligible that it doesn't wind up getting taken into account. Only carbon 12 and carbon 13 do. So what do we do? Well, first thing is we're going to take the, so to get the average atomic mass, we're going to take the isotope mass times its abundance. So again, you got to take it out of percentage. And it is the sum over all naturally occurring isotopes. And that is 0107 at the end. And then you key it into the calculator. And you get an answer of, imagine that, 12.011. So again, I took the mass and I multiplied it by the abundance, not the percent, but the abundance. And I added to that the next one times its abundance. And if I would have had 3, I would have continued. So let's look at another example. Here you have chlorine. Chlorine has 2 naturally occurring isotopes. It has chlorine 35 and chlorine 37. The average atomic mass is going to equal the mass of the isotope times its abundance. This is, and we're going to add to that the mass of the second isotope. Times its abundance. When we do this math, you will see that isotope 35 contributes 26.499 to the overall mass of chlorine. And isotope 37 contributes a mass of 8.953. You add these 2 together, and you get 35.45 technically two, as the average atomic mass. Now, I will say, when you're doing this, I'm not paying attention to sig figs on these problems. The reason I'm not paying attention to significant digits on these problems is, well, the periodic table I gave you has a mass of 35.45 for chlorine. The periodic table up here has a mass of 35.4527 for chlorine. It all depends on which periodic table I'm looking at, exactly how many digits it records. So that's why I don't actually worry about significant digits on that particular problem. If I were to worry about it, it would be 35.45. Questions? Let me give you magnesium to do. then you key this into the calculator. Again, it's their mass times the abundance, and we take the sum over all naturally occurring isotopes. You get a mass of 24.31. One thing I have not mentioned that is important is that the unit here is atomic mass unit. AMU. When when you look at a periodic table, the values on that periodic table are technically atomic mass units. AMUs. Now, I do want to point out something. I actually want to point out three somethings related to your exam. Number one. When you are performing calculations, you should show your work. However, on the average atomic mass, you must show your work. The difference is between should and must. Again, on the average atomic mass, you must show your work. The reason for that is, where is this number? It's on the periodic table. I need to know, do you know how to calculate it? Not just where to find it. So you have to show your work. Now, on the others, I said you should show your work. The reason I say you should show your work is because anybody that knows me knows I do partial credit. But if I don't see any work, I can't give you any partial credit. So that's one of the things I want to point out about your exam. The second thing I want to point out is units. When you give me an answer, you better give me a unit, because a naked value means nothing. And you will have a point taken off simply for not including your units. Units are important because naked values mean nothing. Third thing I want to point out, this is where the exam stops. The next piece of information I go over today is going to be on your next exam. So if you're one of those that makes a line or starts a new page, or however you do it to indicate where exam 1 stops and exam 2 begins, now's the time to do it. I'd say a dozen eggs. What does that mean? 12 eggs. Is it always 12? Yes. Can you have a partial egg? No. When it's a counting number, and counting numbers are exact numbers. The chemist's dozen is a little bit different. We also do have a counting number. The number of decimal places go on forever, but we're gonna shorten it. And the chemist dozen is called a mole. One dozen oranges is 12 oranges. One dozen eggs is 12 eggs. Now, and if I look at those 12 oranges and I have 5 pounds, that's 5 pounds of weight for that dozen eggs. I mean, dozen oranges, excuse me. What we have been discussing when we get the average atomic mass, we've been talking about one atom. So for carbon, one carbon is 12.011 AMUs. For magnesium, one magnesium is 24.31 AMUs. For one iron atom, it's 55.8 AMUs. But the fact of the matter is, we can't manipulate a single atom at a time. We're talking about things that only within the last 30 years have we actually been able to even see. And the only way we can see it is through an electron microscope. We cannot manipulate. The tip of a pen, the tip of a filament is too big to manipulate one atom of anything. So we don't talk in terms of one. Instead, we talk in terms of the chemist dozen. The chemist dozen is called a mole. And just like one dozen oranges has 12 oranges in it, when we talk about one mole, we're going to talk about 6.022 times 10 to the 23rd. Now, that number, I mean, that large of a number in scientific notation is really hard to put into place. So let's use our imagination to understand what a chemist dozen is, if you will. What the mole means. If I take the mainland USA, in other words, minus Hawaii and minus Alaska, if I just take mainland USA and stack it 70 feet high in marbles, I will get 1 mole of marble. That's about, what, 5 to 6 stories tall, all across the United States to get 1 mole of marble. Again, though, it's a counting number, because I can count out that many marbles. It'd take me forever, but I could. So just like we talk a dozen is 12, when we talk about the chemist dozen, which is a mole, we're talking about a counting number of 6.02 times 10 to the 23rd. Now, the nice thing about this is we're no longer talking in terms of atomic mass units. Now we're talking about something we can manipulate, because we can go upstairs and use a balance and get it into grams. And you will notice that the numerical value for atomic mass units and for grams is the same thing. The difference is if we're talking atomic mass units, we're talking about a single atom. Whereas if we're talking about grams, we're talking about 6.022 times 10 to the 23rd of them. Now, if we're talking about 55.8 grams, which is 6.022 times 10 to the 23rd, which is a mole, that means 55.8 grams per mole. That, folks, is called the molar mass. Because it contains both mole and mass. So, if we take the average atomic mass in AMUs, we're talking about one atom of the element. But if instead we take the average atomic mass and discuss it in grams, now we're talking about 1 mole of the element. A mole is a counting number. 6.022 times 10 to the 23rd of anything is equal to 1 mole of that thing. Now, what we've just developed are a couple of conversion factors that can be used. Because now we have a conversion factor that allows us to go from mass in grams to moles. That's one conversion factor. And we have a conversion factor that allows us to go from moles into a counting number. That's the second conversion factor. So, if I am given atoms or molecules, my first step is going to get it into moles, and I'm going to do so by dividing by the 6.02 times 10 to the 23rd. If I want to take moles into grams, then I'm going to work with the moles into grams using the molar mass. So let's see this in action. Calculate the number of copper atoms in 2.45 moles of copper. Okay, I have 2.45 moles of copper, and I want copper atoms. When you start performing stoichiometry, which is chemical mathematics, the first thing you do is ask yourself, is my starting substance and my ending substance the exact same substance? The answer is yes, here. So I don't need a conversion factor for the substance. The second thing I look at is I look at what I'm working with. I have mole. Well, I have 2 different conversion factors that will allow me to work with mole, but I only have one that will allow me to work with atoms. And that conversion factor is 6.022 times 10 to the 23rd of anything. In this case, copper atoms is equal to 1 mole of that thing. So 1 mole of copper. I start with the 2.54 moles of copper. Of that Avogadro's number, the mole of copper goes in the denominator. The mole of copper had to go in the denominator so that the unit and the substance would cancel. The 6.022 times 10 to the 23rd copper atoms goes in the numerator. And you key it into your calculator. And you get a value of 1.475 times 10 to the 24 copper atoms. Now, if we're talking about significant digits, your mole had 3 significant digits. The Avogadro's number has, because this is a number in scientific notation, the coefficient is equal to the number of significant digits. So it has 4 significant digits the way I have written it. And the 1 mole portion is going to be an infinite number of significant digits. So you have 3 significant digits times 4 significant digits divided by an infinite number of significant digits. The one with the fewest is 3. So this answer can only have 3 significant digits. So we would round it to 1.48 times 10 to the 24 copper atoms. On the back of the conversion factor table, there was this flowchart. Trying to think of the name. Right now, you're only going to be paying attention to the one side of the flowchart. We're not going to get to doing both sides yet. What I started with was moles of copper. My conversion factor had to be Avogadro's number in order to get to atoms of copper. So this will help you if you struggle at knowing what to use when. This will help. Let's look at another example. Calculate the moles of carbon in 0.0265 grams of pencil lead. Basically, pencil lead is graphite, which is carbon. So I'm starting out with 0.0265 grams of carbon, and I need to convert that into moles of carbon. I'm starting with carbon and I'm ending with carbon. So I look to the units. I have grams of carbon. Anytime you have grams, your conversion factor is going to be the molar mass. The molar mass of carbon is 12.011 grams of carbon is equal to 1 mole of carbon. Again, anytime you are working with grams, you're going to use the molar mass as a conversion factor. Now, this actually had both units that I need, so I'm ready to do the math. So 0.0265 grams of carbon out of my conversion factor. The gram carbon needs to go in the denominator, so 12.011 grams of carbon will go in the denominator and 1 mole of carbon will go in the numerator. And when I key this into the calculator, I get 0.002206 moles of carbon. Sig figs. In your starting value, you had 3 significant digits because leading zeros don't count. The mole of carbon in the molar mass has infinite number of significant digits. This molar mass has 5 significant digits. So we have 3 significant digits times an infinite number of significant digits divided by 5 significant digits. The measurement with the fewest had 3, therefore your answer can only have 3 significant digits. So you would record your answer as 0.00221 moles of carbon. Again, you can look at this fact. Gram, mole, gram, mole. The only way you can do that is with the molar mass. That's the conversion factor. Yes.
Have this flow chart on the second camera.
You will not have the flow chart. But I will say this. I highlighted something that will help you where you don't even need the flow chart. And that is if you are given grams, you know you're going to have to use your molar mass. If you're given atoms or molecules, you're going to have to use Avogadro's number. So that will help you in memorizing when you have to use what without knowing the flow chart, or you can memorize the flow chart. I just try to help out with multiple tools so that it becomes easier. Yes.
The molar mass is the atomic.
Correct. So that's where it gets tricky. Again, the answer to your question is yes, they are the same number. No, they don't mean the same thing. The average atomic mass means 1. But if you use the exact same number in grams, then you're talking about the molar mass. So it really is dependent upon the unit. But the molar mass and the atomic mass are the same thing. It depends upon what it depends on is how many you're talking about. Let's look at one more example. How many copper atoms are in a copper penny with a mass of 3.10 grams? Assume the penny is composed of pure copper. I am given 3.10 grams of copper, and I want copper atoms. Here's what I was talking about earlier. Yes, I could use this flow chart. Or I can go, okay, folks, I got grams of copper. What does that mean I got to use? I got to use the molar mass. So 63.5 something. 63.5? 546, so 55. 63.55 grams of copper is 1 mole of copper. And what did I say you'll have to use if you have atoms or molecules or ions? I'm going to have to use Avogadro's number. So 6.022 times 10 to the 23rd copper atoms is 1 mole of copper. So we begin with the number we were given, 3.10 grams of copper. You got to use the grams of copper first. Why do I got to use the grams of copper first? Because I got to get rid of that unit. So 63.55 grams of copper is going to go in the denominator with the 1 mole of copper going in the numerator. I put the grams in the denominator because I got to get rid of them. I didn't want moles of copper. I wanted atoms of copper. So I'm going to now use the second conversion factor. The mole of copper is going to go in the denominator because I got to get rid of it. And that's going to put the 6.022 times 10 to the 23rd copper atoms in the numerator. Now I'm ready to do my math because I got the unit I wanted. I got atoms of copper. And I get a value of 2.9376 times 10 to the 22nd. I started with 3 significant digits. The molar mass, the mole portion is infinite, while the mass portion had 4 significant digits. The Avogadro's number has 4 significant digits because it has 4 digits in the coefficient, and it is an infinite number in the denominator. The measurement with the fewest is 3, so I need 3 significant digits in my answer. So that would be 2.94 times 10 to the 22 copper atoms. Questions? We will do more when I pick up on Tuesday of next week, just to get your minds rolling on this stuff again. And then we're going to move into energy and start talking about quantum numbers and the shapes of atoms. I will see you Thursday for an exam.